Good morning. Sorry for the delay. It took a while to get the computer going and now it kicked my iPad out, so I have to give it a minute to let it get loaded again. Let's see, we've got everybody but Clara Jane. Let's see, Lucas is coming in. There's Lucas. All righty. So maybe Clara will join in just a minute. But anyway, let's go ahead and quickly do a little review of what we looked at last week. We started this new chapter dealing with transformations. So just kind of going back to 7.1, we learned about transformations, and basically a transformation is some type of movement of something we call a pre-image. Remember, the pre-image is where we started. And then after it has done some kind of movement, that new image is called, that new one is called the image. So it starts as a pre-image. Once it moves, we call it the image. So usually when we have a pre-image, whether there are points on a line or if it's a triangle or whatever it is, what kind of shape it is, it will be described with some type of capital letter. And so then we said once it goes from pre-image to image, then we describe that using a prime symbol. Did somebody get kicked out? Or do we have, who did we lose? We lost, no, April's still here. Okay, here comes Alec, but we lost Alec. Hold on a minute. Okay, we got Alec back.
Sorry, it lagged me out.
That's okay. That's why I'm having computer problems, and I can tell that mine's lagging because my screen keeps freezing. And like I said, it kicked my iPad out when I was trying to link it up. So we're going to give it a little bit of time. So anyway, just all kinds of computer problems. The computer thinks it's Monday. But anyway, so we talked about that we have three main types of transformations. We have what's called a reflection, and that's the one we talked about as like a mirror image. That's where it starts out as one way and it can flip. Either a lot of times if we're talking about the coordinate plane, it might flip side to side over the y-axis, or there may be a different plane that they tell it, a different line on the graph to tell us to reflect over, or it can reflect over the x-axis, or it can rotate about the flip, depending on what they tell you to make it reflect over. Okay, so basically a reflection is a mirror image. I think of it using the word flip. Okay, so reflection and flip are going to be the same thing. And then with the second one we looked at was called a rotation, and a rotation is a turn. Okay, so thinking about, usually it's going to rotate about a point. Okay, so we have what's called the point of rotation, and sometimes our figure can be outside of that point and it can rotate about that point, or sometimes our figure can be located on that point, and when it rotates, it's rotating on that point. Okay, and like I said, these are the things that we're having to really focus on. And now we've lost Easton. We have to really focus on and do a lot of mental images. Oh, here comes Keely. Let's see. We're just struggling today. So hold on a second. We'll get Keely in here. And then I'm assuming Easton's going to come back. Clara's usually always here, and I don't think I've gotten a message from her. Nope, I don't see anything from her yet. Good morning, Keely. Let's see if we can get, I don't know, this one that says reconnecting. I don't know. I guess that's Easton. There's Easton. All righty. Now we got everybody at Clara, but we'll hopefully she'll log in a bit. Okay, so we were just doing a quick review about our transformations. We talked about a reflection. Now we're talking about a rotation, and it rotates around a certain point. And it can either be rotating about that point or actually rotating on that point. And then the last one is a translation. And we said a translation can be thought of as like a slide, how it starts at one point and it just looks like it has just slid either from side to side, up and down. It can go diagonally, however it is. It stays in its exact, it's oriented exactly the same. It doesn't turn or twist or flip or anything. It just looks like it has just slid in the exact same position it was originally in. Now, one of the things we talked about how all three of these are what we call isometries. And we learned that an isometry means that from pre-image to image, it is exactly the same shape. It is exactly the same size. My lengths of all my sizes are sides are the same. My angle measurements are all exactly the same. Nothing changes as far as the shape of the object goes, but the only thing would be is if it flipped, then it would be a reverse image or something like that. But nothing about the shape of the object has changed or the size of the object. It's not one is smaller and now it becomes bigger, or one was bigger and it becomes smaller. It's all exactly the same. Okay, so that's what it means when it says it's an isometry. Okay, so then we moved on to 7.2, and 7.2 was where we focused on reflections. And we talked about, again, that a reflection, it can reflect over a certain line to where you can see where it's clearly flipped over it, or where it's on a point and it has just flipped on that point. So obviously if a point flips, it's still a point. It's kind of like flipping an equal sign. It looks like an equal sign either way. Same thing when I have my my pre-image on a point, and then if it flips on that point, it still looks exactly the same. But the way that we can tell that there's been a reflection is we look at that capital letter that's by itself, and then we can see the capital letter with the prime symbol. So therefore we know it is both a pre-image and an image when it has that prime symbol. Okay. Let's see. The main thing about a reflection, whenever it reflects over a line, is if you can identify the distance from my original pre-image to the point, and to the line of reflection, if I look at that distance from one side, then I know where my distance is going to be on the other side where it has reflected, especially if it's on a coordinate grid. Okay. And then in 7.2, we went on to look at a line of symmetry, and lines of symmetry are things that we probably started learning about like I'm trying to remember when I was little. I can remember drawing pictures, lines of symmetry, and I can remember being in elementary school and folding a piece of paper in half. So we had that half and we had to draw an image on one side and we had to match the exact image on the other side. And so lines of symmetry are things that we start learning about when we're little. We just don't know exactly what it is. And the last thing we think of is that, hey, I'm going to see this again in geometry. But anyway, it's something that we've worked with since we were little. And we know that sometimes things may have no line of symmetry. There may be nothing that reflects from one side to the other or top to bottom. But like on page 406, that's where we learned that even a hexagon, we have 3 different shapes that are hexagons, but we can see that depending on the way that they're drawn, letter A only has 1 line of symmetry, where if I cut it from top to bottom, B has where I can actually cut it from side to side and top to bottom, and then C ends up having 6 lines of symmetry. Okay, so if it is a regular polygon, remember we talked about a regular polygon has the same length of sides, same angle measures. So if it's a regular polygon, it's going to have the same number of lines of symmetry based on its number of sides. So since a hexagon has 6 sides, then it's going to have 6 lines of symmetry. Okay. All righty. Then we moved on to 7.3 rotations. And so this was the one where we talked about how it has that point of rotation. And we talked about when I have the figure, like the example they gave us was the flag. When I've got the flag and it is rotating, it's rotating about a point. Okay, so if I've got my flag and it rotates, it's going around that point of rotation. Now remember, it can go clockwise or counterclockwise, but also from whatever those 2 points are, I can draw a line from each point, like on my flag, the end of my flagpole, I could draw a line to that point of rotation. And then when I've got from my pre-image to my image, when I connect those same points, it actually makes an angle. So we learned about the rotation can actually form an angle. And so we can look at that movement. And so if I've got 2 points on my segment or my figure, when it rotates around, I can actually make 2 different angles. I can go from my bottom point to my point of rotation, and then it goes over to my image, or I can have my pre-image top point, draw an angle down to my point of rotation, and again, make that to my image. And both of those angle measures are the same. And that's where we said that they're both, we can look at them and it's going to be X degrees, because depending on how big of a rotation it is will determine the degree measure of that rotation. Okay, so again, we talked about how I can have my figure and I can draw the lines. Now, sometimes I have a figure and it lines up and I have collinear points. And so then when it rotates, it actually ends up making one big angle. Okay, and then we also talked about how if I've got my figure and it's actually on the point of rotation, then it can kind of go like that. So that's at the bottom of 412. Okay. One of the things that I strongly encourage you to do, especially with rotations and everything, and also one of the things that we're going to be getting into is where we're actually doing a couple of transformations put together, and we're having to really visualize these. So if you're struggling with being able to picture these in your mind, draw a picture on paper and cut it out. Okay, if you need something more concrete. Yesterday I was working with somebody and I found a Lego on a table or something. And I'm like, okay, so this is your rectangle. So when it turns like this, it doesn't have, so get concrete objects to where you can actually visualize these things if you can't picture it in your head. Because that to me is the biggest challenge with each of these things. Is being able to look and think about, okay, if it turned this way, or what if it flipped and then it turned, all that stuff. So get concrete objects if you need to do that to help you. Okay. All right, so rotation, same thing as a turn. And we also looked on page 414 and we talked about how a rotation can also be looked at, especially if I have 2 intersecting lines. Okay, I've got 2 lines that have intersected, that actually a rotation can be looked at as a flip over each of the lines. So we learned that if it flips over one line, or if it reflects over one line and then reflects over the other line, it's a rotation. And so that was the part where we talked about, so then it has reflected, it has moved X degrees, and then it reflects again. So then that would be X degrees. So it has actually gone 2X degrees. So that's what we had on page 414 with theorem 7.3. On page 415, we talked about rotational symmetry, and we talked about how an item has rotational symmetry if it can rotate anywhere from 0 to 180 degrees and still look exactly the same. So that was the box that they gave us, or the little square that they gave us on 415. Okay, so let's see, rotational symmetry real quick. Let me find something, or something on my table. I guess we'll just go with a book. Okay. So basically, if I've got this book and it's in this direction, if I go 90 degrees, it's up and down. So it's not the exact same as it was at this location. So at 90 degrees, it does not have rotational symmetry. We're going to pretend like it does not have these words and images on it. It's just a rectangle. But if I go 180 degrees, it's still same length and width. So it does have rotational symmetry at 180 degrees. It does not at 90 degrees. But if I had a perfect square, which I don't think I do, if I had a perfect square, ooh, we can use this and pretend like the wire's not on it, okay? Like this. So if I have it here and I turn it here, it does not have, so I've got that rotation. But when I go this way at 90 degrees, it still looks exactly the same as it did when it's here. And then I can go 180. Again, it's the same. So that's what it's talking about, rotational symmetry. Rotational symmetry is, can I make it turn less than 180 degrees, and it looks exactly the same. Okay, that's talking about. All right, 7.4, we get into translations and vectors. And so get ready. I think 7.4 was where we left off. So any questions from homework in 7.1, 7.2, or 7.3 so far? Let's start with 7.1. Here comes Clara Jane. Give her a minute to log in. Good morning, Clara.
Hello.
We were just doing a quick little review of where we've been in chapter 7 so far, and we're getting ready to answer any questions about homework. So we're starting with 7.1. Are there any questions on homework in 7.1?
33 and 35.
33 and 35, okay. All right, so it says in 33, it says, show that the transformation is an isometry by using the distance formula to compare the lengths of the sides of the triangles. Let me see if I can get my iPad to hook up again. Hang on just a second. Now remember, distance formula. You've got the square root of the difference of the x's squared plus the difference of the y's squared. And so let me get this real quick.
Oh yeah, quick question. Did anybody else get snow?
We didn't get any, did y'all?
I did. Yeah,
You
it's
did?
covered up everything.
Oh, wow. Yeah, we didn't get any. There we go. And then real quick, while I'm thinking about it, Easton, I need your chapter 6 test. I haven't gotten it yet, and I've looked through my email. So if you sent it and I just have missed it somewhere.
Didn't I hand it into you when we did homework on Thursday? Or did I not?
I don't think so. The chapter 6, because I gave you guys because I sent it to you guys over the holidays. Because we did the chapter 5. I gave y'all chapter 5. So did you give me chapter 5 corrections? Because I also need chapter corrections, also chapter 6 corrections for those of you that I've sent. So look for it and see, because I emailed y'all the chapter 6 test. So it was over the holidays. Okay, let me get a sheet of paper real quick and we'll do this problem. All right, so remember that with the distance formula, I've got the square root of x2 minus x1 squared. Whoop. Let me rewrite that. Well, it's bigger. All right. Square root of x2 minus, why did I have to put it at the top? Minus x1 squared plus y2 minus y. Okay, so that's our distance formula. So what I've got to look at in number 33 is when I started with, you can see that my pre-image is triangle ABC. So when I look at letter A, I'm going to go ahead and write down my points. So A is going to be -2, 1. So I went 1, 2, 1, 2. So I've got A is -2, -2. B is 1, 2, 3, 4, 5. So -5, 1. And C is going to be 1, -2, +2. Okay, so what I'm having to show here is that AB, I'm going to have to find my lengths for each of these. So I start with, and so I'm going to look at the distance of, here, let me do this. I'm going to look at distance of AB. So now I'm going to have, so let's see, x2 will be 0.1. So 1 minus a -2 squared plus -5 minus -2 squared. So I have 1 minus a -2, that's the same as 1 plus 2, so that's going to be 3 squared plus -5 minus a -2 would be -5 plus 2, so that's going to be -3 squared. So 3 squared is 9, and -3 squared is also 9. So that's going to be the square root of 18. Now remember, I want to simplify as much as possible, okay? So the square root of 18 is the same as 2 times 3 times 3. So this is where I say I've got 2 3s under here that can come out as a whole number, and then I have the square root of 2 left under my radical. So the length of AB is 3 times the square root of 2. Now I'm going to have to do the length of BC. BC, I'm going to have 2 minus 1 squared plus -2 minus a -5 squared. So 2 minus 1 is 1 squared plus -2 minus a -5 is -2 plus 5. So that's going to be 3 squared. 1 squared is 1. 3 squared is 9. This is the square root of 10. So 10, when I break that down, my prime factors are 5 and 2. There's nothing that can come out. So that's going to be my length of BC. So AB is 3 times the square root of 2. BC is the square root of 10. Now I've got to look at AC. So I'll come over here. I'm looking at, or CA, whichever one you want to call it, but we'll call it AC. So now I'm dealing with A and C. So I'll have 2 minus a -2 squared plus -2 minus a -2 squared. So 2 minus a -2 is going to be 2 plus 2, which is 4 squared plus -2 minus a -2 is going to be -2 plus 2. So that's going to be 0 squared. Obviously, 0 squared is 0. So then when I say, where did I mess up here? Did I get my right numbers? -2 minus a -2, -2. One, two. I've got 2 minus -2, so -2. Okay, so I've got 4 squared is 16, so that equals 4. All right. So now I can see the length of all of my sides of my image, my pre-image. Now I've got to do the same thing with my image. So now I'm looking at X, Y, Z, X, Y, Z. So my ordered pair for X is going to be 0, 1, 2, -2. Y is going to be 1, 2, 3, 1. And Z is going to be 0, 2. So then I go through the same process, okay? I'm not going to take the time to do that right now, but I just wanted you to see the process with the first triangle. The process with the second, I find that X, Y is equal to 3 times the square root of 2. I find that YZ is equal to the square root of 10, and I find that XZ is equal to 4. So I can see that AB is equal to XY, and those both equal 3 times the square root of 2. I can find that BC is equal to YZ, and that equals the square root of 10. And then I find that AC is equal to XZ, and those are 4. And since all those have these same measures, then I know, because the distance is the same, then they are isometries. Because remember, in isometry, the distance maintains the distance stays the same. So that's what you had to do for 33. Okay. Now number 35. When we look at that one, I can see I've got different angle measures and different side measures for each thing. And remember, because they're isometries, they should be equal to each other. So in number 35, you can see that my angle measure that they're showing me is 2W, and the angle measure that corresponds with it is 70 degrees. So 2W equals 70 degrees. Therefore, I divide by 2 and divide by 2, and W is equal to 35. Okay. Then with X, I can see that my side that corresponds with X is 14. So 3X plus 1 equals 14. Subtract 1. 3X is equal to 13. Divide by 3, divide by 3. X is equal to, so on this one, I'm going to go ahead and I can either leave it as an improper fraction, or so I could leave it as 13 over 3. I think the book went ahead and changed it to 4 1/3. They put it as a mixed number. And then finally, my other side, 6 equals 2y. I can see where those sides correspond. So divide by 2, so y is equal to 3. So you have to know the definition of isometry, meaning that they are equal to each other. You look for your parts of your figure that is equal to one another and create an equation with an equal sign. This is equal to this, and then I solve. Okay. Any other questions from 7-1? All right, how about 7-2? Let's move on to 7-2. Any questions on 7-2? All right, then let's move to 7-3. Any questions on 7-3?
I got a couple.
Okay, what you got?
On page 418, 31 and 33.
31 and 33. Okay, so let's take a look. So on number 31, notice that I've got what is a rotation, but notice where we start in the blue, and we can see where we go from blue to red to green. So we can see that actually in this situation, we really don't have to focus on that much, because we're just talking about the angle of rotation. And look back at Theorem 7.3 on page 414. It tells me that the angle of rotation, when I have two reflections that make a rotation, equals 2x degrees, 2 times x degrees. So in number 31, they've told me that one rotation, that x is equal to 15 degrees. So 2x is equal to 30 degrees. And that's all it is they told you that 1 degree was 15. So if I know that my angle of rotation is equal to 2x degrees, then I'm just multiplying 15 by 2. Does that help? Okay. And you said 35?
Yes, ma'am.
Okay. So again, on 35, I'm doing the same thing, understanding that it's an isometry.
My bad, it's 33.
33,
Sorry.
okay.
I also have a question on 35.
You do have a question on 35? Okay. So let's do 33, then we'll have then we'll go 35. So let me change this. So number 33. Okay, so 33, it says lines M and N intersect at point D. So it says consider a reflection of triangle ABC in line M followed by a reflection in line N. Okay, so I'm just going to go ahead and draw random lines. And I'm going to say this is M and this is N. And they intersect at point D. And we know that we have triangle ABC that reflects line M. And then it reflects on line N. Okay, so it says that if the angle of rotation equals 162 degrees, okay, think again, we just talked about how my angle of rotation is 2 times x. So that means that 162 is equal to 2x. So I'm just going to divide by 2, and x is equal to 81 degrees. And that's all it is there. So it's basically doing, I'm taking my whole angle of rotation and having to show what the degree would be for one reflection. So I'm having to divide that by 2. Whereas the previous one, I had one of them and I had to show it for the whole thing. So I had to multiply by 2. Does that make sense? Okay. Now let's look at 35. Okay, 35, again, the same thing. We have been told that a rotation is an isometry. So I know that each corresponding side measures are going to be the same. I know that each corresponding angle measures will be the same. So what I'm going to do is I know I'm having to solve for, we've got several things to solve for. Let's see, I've got Q, R, S, T, and U. So I'm going to go ahead and write Q, R, S, T, U. I'm having to solve for each of these. So I'm going to start by looking at Q, okay? So on Q, it's telling me that that whole entire angle is 60 degrees. So that means that for Q, I know that 2 times Q equals 60 degrees. So divide by 2, and Q is going to be 30 degrees. For R is going to be, and again, remember, well, I guess they haven't done all these points. So I'm having to look at my corresponding sides so I can see that for R, I have 2R is in my equation, and 2R corresponds with the number 10. Let me move it over here. So it shows me that 2R, my side 2R is the same as my side that equals 10. Divide by 2. So R equals 5. Side S is equal to the side that measures 11. So S is 11. T, my side that has 3T, is equal to the side that is equal to 3. Divide by 3, so T equals 1. And then U, my side that has U, I've got 2U equals 4. Divide by 2, so U equals 2. The main thing about this, again, is understanding that because it's an isometry, whatever side corresponds with my side and my rotation, they are equal to each other. Therefore, I can set up an equation and solve for the variable. Any questions about that? You good, Easton? Okay. All righty. So that was 7.3. Any other questions from 7.3?
I actually have a question on, I guess it was 27 and 29.
Okay.
Just on the page before.
Okay. So let me flip back to that. All right. So number 27. It says, name the coordinates of the vertices of the image after a clockwise rotation of the given number of degrees about the origin. Okay, so one of the things that we have to think about is when it talks about something rotating about the origin, remember that is my point of, that's going to be my point of rotation. And so when I think about it rotating around, let me flip back real quick and let's take a look at. Okay. So when we look, let me get, actually, let me change my paper. So basically in this one, actually, I don't know I'm doing this. Let me go to, well, yeah, I do need to do that. 1, 2. So we said this is E. 1, 2, 3, 4, 5. And then 1, 2 is F. And then 1. Is D. Okay, so here's where we started in that figure, okay? And so it says that it's going to go a 270-degree rotation. So think about, and it's going about the point of the origin, okay? So what I'm thinking about here is, let me go ahead and draw, actually, let me change my color there. It says it's rotating about the origin, okay? So think about if I was doing, if we, the example for this is example 2, okay? So if we go back to example 2, we can see where this one was a 90-degree rotation. So think about when I go from one point to the other, if it's going 90 degrees, then that I know that my from my point of rotation to my one, each point is making a 90-degree angle, okay? So in this one, and so think about how an 180-degree rotation is going to be a straight line. This one's 270, so that means I'm going 180 degrees, and then I'm going an additional 90 degrees, okay? So that means not only am I going here to here, but now I am going again up to, so I've got my, oh, so if that's a 90-degree, then I know, so that would be like a rotation, well, why can't I get it to right? Okay, we've got 90 degrees, then 180 degrees would go there. And so 270. So now we're looking at, this would be a 270-degree rotation, okay? So then when E would rotate around, we can see that E now, instead of being at 2, 0, okay, no, we started at 0, 2. So when it rotates around, hold on a minute. It's actually going to stay in its same place. Or I guess I didn't label these. I should have done that. 2, 0 is there. Let's see. We said that F is 1, 2, 3, 4, 5, -2. And we said that D was 1, 2, 3, 4, -4. Okay. So when it makes that rotation, then now what was 2, 0 now has rotated and it is at 0. Whoop, wrong place. This point has rotated around here 270 degrees to 0, 2. Okay. So then F also rotates to 270 degrees. So now when it rotates around, so when we look at this, when it rotates around, it actually comes around, and when it goes around 270 degrees, F ends up at 2, 5. 1, 2, 1, 2, 3, 4, 5. And then when D rotates around, it ends up being at 4, -1. So when I go 1, 2, 3, 4, no, 4, +1, 1, 2, 3, 4, 1. Okay, so thinking about that movement, we notice that E, or actually we'll start with D. D started out as 1, -4. And when it translated 270 degrees, it became 4, 1. So, and then E started out as 2, 0. And when it reflected, it became 0, 2. And then F started out as 5, -2. And then it became 2, 5. So look at that pattern there. Okay. Do you notice how we started out with 1, -4, and it flip-flopped to become 4, 1? If we look at the pattern over on example 2 at the bottom, it says this transformation can be described as X, Y, and it becomes -Y, X. Okay. So here, we're looking at the pattern that this one transformed to, and we started with X, Y, and it transforms to where you can see that 1 was my original X value. It became my Y value this time. -4 was my original. It became a +4. So it's following this same pattern right here, where if I started with 1, -4, I'm going to take the opposite of -4 and put it here. So it becomes positive. And then whatever was X ends up in my second location. Okay. I think I went kind of a very long way around trying to show you visually, but the main thing is if you're looking at that pattern, you can see where the rotation of it ends up. We've got a pattern here of whatever XY is, then it becomes -YX. Okay, so if I look at what those points started out at, that's what they shifted to. And then we had what other number was it? 30 or 20?
29.
29. Okay, so think about 180 degrees again. So 180 degrees. We also, so think about its straight line 180 degrees. So when it shifts around, basically it's going to end up, let me just draw it real quick. Okay, so on this one, we started out with 0.0. No, is that an O? Yeah. O is at our origin. So we've got 0, 0. And then X is 1, 2, -2, 1, 2, 3. So -2, -3, 1, 2, 1, 2, 1, 2, 3. Whoop. We said that was -2, -3. And then Z is going to be 1, 2, 3, 1, 2, 3, 4. So 3, -4. 1, 2, 3, 1, 2, 3, 4. Okay, and that is Z. So that was O. 3, -4. So basically, if we were to have a shift around, okay, and we are going 180 degrees, we know that when we shift, that if we went, that we're basically going to end up, well, obviously this one's going to rotate 180 degrees on this point. I've got this one, X is going to rotate 180 degrees. Whoop. And Z is going to rotate 100. Whoop, I'm just drawing terrible. It's going to rotate 180 degrees. Okay. So again, this is one of those things where being able, I mean, I'm such a visual person, and that's why I'm having trouble kind of trying to tell you how to visualize it. But basically, when it shifts around, I know that Z, that it's basically upside down. And so Z is now shifting to where this right here, I know is going to end up over here. Okay. And so since it's going 180 degrees and I know it's going to end up over in this location, what I'm doing is I'm looking at these ordered pairs to say, all right, so if it shifted to that location, then how are my numbers going to shift to get it in that location up there? Okay. So I know that when it goes over there, I know that now my X value is going to have to be negative, but my Y value is going to have to be positive. So if I take the negative of X and the negative of Y, because since this one here is positive,
Jennifer?
negative. Yes.
I'll be right back.
Okay.
It's
So
at the
since
moment
this-
it's hailing outside.
Huh?
There's
Okay.
hail outside right now.
Oh, goodness. So when I'm doing that 180 degree rotation, I can see that my point is going to have to land over here. Over here, that means X is going to be positive. X is going to be negative and Y is going to be positive. So if I change 3 and it has to become negative to be on that side of my line, I know I'm going to have -3. -4 down here is going to have to become positive. So up there, it's going to be a +4. So then I can go 1, 2, 3, 1, 2, 3, 4. And let me erase this up here. So 1, 2, 3, 1, 2, 3, 4. This is where my Z location is going to be. And it's going to be -3, +4. This guy is staying here. Because he's rotating on his own point. Then I know that X is going to have to end up on this side over here because it's going 180 degrees. So again, for -2, -3 to transform over here, then my -2 has to become positive. So I'm taking the opposite of -2. So I'm having to do the opposite of X and the opposite of Y. So for -2, its opposite is going to be +2. And the opposite of -3 is +3. 1, 2, 3. So then I'm able to look at that, and that would be 180 degree rotation. So now this one is 2, 3. So basically what I'm looking at is based on where the rotation occurs. That may be, and actually that may be something that's easier to kind of to visualize. If my figure rotates a certain number of degrees, which coordinate is it landing in? What did its original ordered pair start in? What coordinate is it landing in? So using those same numbers, how do they shift, or what's that, what is our change with our numbers? Is it a negative X? I mean, am I taking the opposite of X and the opposite of Y? Do I only take the opposite of X and Y stays the same, or X and Y flip-flopping? So based on whatever those rotations are, I can look at those patterns. And once I see the pattern for one, I'm just using the same pattern for every single ordered pair. Okay, does that help, or did I make it more confusing?
That helps.
Okay, so just thinking about looking at what when I make a rotation, if it's going 90 degrees, I've shifted to one coordinate, 180, 270, whatever it is, I'm looking at where it's shifting so I can find that pattern and have my numbers, okay?
Yes,
All
ma'am.
right.
Thank you.
Any other questions on 7.3? All right. Obviously, we have gone over our break time, so let's go ahead and take a break, and then we're going to come back and continue working on 7.4, where we left off. So go ahead and take a 5-minute break. All right, so as we're coming back, you can see that I've pulled up my notes from 7.3 and I've added a couple of them on there that'll help you. They only gave us the 90-degree rotation in the book, so I went ahead and added the 180-degree rotation and a 270 rotation, so it's not as confusing and having to visualize and go through all that we just went through trying to solve those. We have formulas that are given for these. So go ahead and add these to your notes for 7.3 for rotations. You can see that from the book, we had the 90-degree rotation where we started with X and Y, and then a 90-degree rotation, which it would be in the order of negative Y then X. That would be the pattern I would follow for each new ordered pair. 180 degrees XY becomes negative X, negative Y. And then a 270-degree rotation becomes Y, negative X. Okay, so if you just go ahead and learn these, then that'll be something that you don't have to go through or be able to look back at them when you're doing your work to be able to see the pattern. It'll be much easier than what we just went through trying to go to the grid, rotate it, think about, okay, 90 degrees is going to put you here, 180 will put you here, then having to go through all of that. If you just have the formulas to look back at, then that will help tremendously. Okay. So just go ahead and add those to your notes if you haven't already. All right, we ready to move on, or is anybody still writing?
I think I need just a second to finish writing them down.
That's fine. So add these to your notes on 7.3. The main thing to remember is like when it goes from XY to negative YX, think of that negative as the opposite of, okay? So obviously if it starts out, if one of the values X or Y was already negative, the negative of the negative is the positive or the opposite of the negative. So don't look at that and go, oh, well, it says it's got to be negative Y, so it's got to be a negative number. No, it just means the opposite of. So when you start with XY, a 90-degree rotation ends up being the opposite of Y and then X. 180 degrees starts out as XY, so that we have the opposite of X, the opposite of Y. 270 XY starts out, then it goes to Y, and then the opposite of X. Okay? All right, are we good? All righty. So moving right along. So we got partway through 7.4 talking about translations. We talked about how our translation, basically it's a transformation that maps onto itself every time. So each time we've got that mapping on each way that it's going. When we talk about mapping onto itself, it means it's just like it's the same image on itself for every, like if it moves a whole bunch, then I've got a whole bunch of mappings onto itself, because every time it shifts sideways, it's right on top of itself. So we learned that it says a translation is a transformation that maps every 2 points P and Q in a plane to points P prime and Q prime. So the following properties are true. So this was on, let's see, starting on page 421 at the top. So we learned that P prime is equal, P prime is equal to QQ prime. We also learned that PP prime is parallel to QQ prime, or segment PP prime and QQ prime are collinear, okay? Then we learned that based on the translation theorem, that a translation is also an isometry. So all those rules about isometries are true for a translation as well. You can find the image of a translation by mapping a figure on a plane. Another way to find the image of a translation is to complete one reflection after another with two parallel lines. So remember, with our rotation, we did two reflections over intersecting lines. So that's the main difference here between our rotation and our translation, is with our rotation, it reflected twice over intersecting lines, whereas now we have 2 reflections over parallel lines, okay? So it's very similar that we have 2 reflections. The difference is rotations are around intersecting, translations are over parallel. All right, so theorem 7.5 at the bottom of 421. Theorem 7.5 says if 2 lines are parallel, then a reflection over each line is a translation. If P prime prime is the image of P, then the following things are true. Then we can see where line P prime prime is perpendicular to the 2 parallel lines. P prime prime is equal to 2D, where D is the distance between those parallel lines, okay? So P prime prime is going to be 2 times that distance. So again, remember earlier when we had 2 times the degree of the angle measure, we had 2x degrees for a rotation. Now we're doing 2 times D because it's twice the distance between our parallel lines. It says translations in a coordinate plane, starting on page 422. Translations in a coordinate plane can be described by the following notation. XY translates to, so I'm right here, X plus A. Why did I do B plus Y? That should be Y plus B. It really doesn't matter, but anyway, Y plus B, where A and B are constants. And so the constant A tells me, am I going right or left? So when I add A to X, that tells me, am I shifting X left or right based on what that number is? If it's positive, I'm going to the right. If it's negative, I go to the left. And then my value of B tells me, am I going up or down? Okay, so B tells me up or down. So if I start with XY, then X plus 4 means I'm going to the right 4. And B minus 2 tells me I'm going down 2. So when I started with XY, I'm going to move X from where it is, I'm going to go right 4. And B is going to go down 2. So that tells me where to plot my point. All right, so now we're starting with another way to describe a translation, and this is at the top of 423. I'm now at the top of page 423. And it says another way to describe a translation is to use a vector. So the word here is vector, which is a quantity that has both direction and magnitude. So both direction and magnitude or size, and is represented by an arrow drawn between 2 points. So another way to describe a translation is to use a vector. My vector has both direction and magnitude. Another way to describe magnitude is size. And we represent it with an arrow. Now, if you look, the arrow is a little bit different than when we do array. Think about array. If I had ray PQ, notice it's got this second part of the arrow at the bottom. But notice here, my arrow only has the top part. So that's a very small difference with my symbols. But I can see when it is missing that bottom part, my little pointy part right there, when that is not there, that is describing a vector. This describes a ray. Now, I will tell you, a vector and array are they look exactly the same. I have an endpoint and it goes indefinitely. So don't stress too much about that. I just wanted you to see that there is a little bit of a difference, but it's not a huge deal, okay? Because we're treating it basically the same way. All right, so when we're looking at page 423 and we see that vector PQ, okay, so I can see that vector PQ. Notice that when they look to see real quick, what I'm going to do is flip back to my book for just a second. So notice here, I've got my vector PQ. This is my end point right here, okay? Notice that what they've done is they said, hey, I move 5 units to the right and 3 units up to make my vector into a triangle. Okay, so basically when I'm looking at a vector, I've got my initial point. So with array, we call it an endpoint. So here we're calling it an initial point. So this is my initial point in array. And then we call it a terminal point at the other end. Okay, so the side with the arrow is called the terminal point. But notice when I'm working with a vector, I'm looking to see basically just kind of a simplified way. They don't say this in the book, but this is, y'all know that I come up with my own ways to kind of think of things. When it's talking about its component form, and I'll flip back to notes in a minute so we can fill that in. But when it's talking about the component form of the vector, basically it's saying how many places to the right or left do I need to move, and how many places up or down do I go to make a triangle with my vector. So remember, since X tells me side to side and Y tells me up or down, then I'm going to start with my side to side movement. And you can see also we use this instead of parentheses for my ordered pair. I've got kind of pointy, kind of like really wide, greater than or less than signs. So you can see that because I had to move 5 places to the right, then this number is +5. And I had to go 3 units up, that is a +3. So in a sense, I'm thinking about with component form, I'm thinking about what do I have to do to turn that vector into a triangle, a right triangle. Okay, let me go back to my notes and we'll fill these in. Okay, so where we left off, we said it was an arrow drawn between 2 points. The starting point of a vector is called the initial point. And the ending point is called the terminal point. Remember, that's the point with the arrow. So it says an example vector PQ. P is the initial point and Q is the terminal point. And then it says it has our picture with the symbol in PQ. It is just read as vector PQ. So when I see that little arrow, I see the arrow symbol that doesn't have 2 sides, then I know it's a vector instead of array. Hang on just a moment, I'll let my dog in. Okay. Now it says the horizontal component of a vector is the number of units to move left or right from the initial point. So horizontal, left or right from the initial point, and the vertical component is how many units to move up or down to get the terminal point. So I'm going to make a little note over here that says, think about how to turn vector into right triangle. That's the way it kind of helps me remember. When I'm talking component form, I've already got the hypotenuse of my right triangle. So how many places do I move to the right or left? How many places do I go up or down to be able to make that vector turn into a right triangle? That helps me to identify component form. Okay, so then it says the blank of a vector combines the horizontal and vertical components so that a vector has a horizontal component of 5 and a vertical component of 3. So this is called my component form. Again, this is one of those things where geometry has its whole new set of vocabulary. It's all brand new. We're trying to tie it back to things that we previously have learned to be able to understand it better. So if you cannot remember these vocabulary terms, it's going to be in your best interest, again, to make flashcards, to just rewrite notes, just to practice these terms to help you remember what they mean. Because it's the kind of thing where you can't expect to learn new information and have it stick if you don't practice with it. Just like if when you first started learning to solve for X and you had 3X plus 5 equals 19 or whatever, you had to practice continually. I've got to subtract and then I've got to divide, or I've got to do whatever I do to be able to solve for X. You weren't expected just to immediately go, oh, this is how you do it, and then you better remember it every single time. You had to practice and learn it and practice and learn it. Same thing here, okay? It's a brand new set of terminology, so you've got to just take some time to learn it. Okay, so our assignment for this section is pages 425 through 427, numbers 15 through 33 odds. And then we also are going to do numbers 39, numbers 41, 45, and 47. Okay. All right, so if we look at 15 through 33 odds, should be fairly self-explanatory. If you notice that for 25 through 29 odds, notice that it gives us the translation. It's starting out as XY, and then it says I'm going to have to add 12 to X and subtract 7 from Y. And all you're doing is giving what would the component form be? What are my new coordinate points if I subtract, or if I add 12 to X and subtract 7 from Y? That's all that is telling me to do there. Number 39, let's see. Number 39, we have a figure. And so it says to use a straight edge and graph paper. A straight edge is just a ruler, okay? So if you have a ruler, great. If you don't, use an edge of a piece of paper just to try to connect your points. Or if you're really good at drawing straight lines, don't stress about that. So basically, you've got your figure, and then it says that it wants you to translate triangle ABC to the given vector. So if my component form is 2, 4, that means that I'm starting with my triangle wherever it is in number 39, and I am going to go right 2, up 4 for each ordered pair and graph the new figure. Okay, that's all you're doing in that one. Same thing with 41. You've got your original figure, and then that means you go to the left one and down 5 for your new figure. 45 and 47, you can see where I have multiple choice. I have choices A, B, C, D. And so it is saying, okay, I'm giving you new ordered pairs now. So which component form does it match? Okay, so that's what you're looking for in 45 and 47. All right, we are going to move along to 7-5. For some reason, I've got an extra page in there. I don't know why it didn't. All right. Okay. So 7-5 in your notes. Did I send y'all 7-5?
I don't think so.
You do or do not?
No, ma'am.
I didn't
Okay.
get.
Why did I not do that? All right. let's go ahead and take a look at 7.5. What I will do is I will fill these out as we go. So you're going to be looking at your text and I will send these to you already completed. How about that? So let's go ahead and look at 7.5. And then as soon as class is over, I will send y'all this page with the blanks filled in. So we're starting on page 430 and it says glide reflections and compositions. So it says a translation or glide and a reflection can be performed one after the other to produce a transformation known as a glide reflection. Okay. All right, something has happened because this says theorem. Hold up. That for some reason that's a repeat. I don't know what I've done with these notes. Hang on just a minute. Seven, 4. Where in the world is 7? I think what I did is I had 7.5 right there. And I thought it was theorem 7.5. And I think I made notes for 7.5. Y'all, I'm losing my mind. But y'all have already known that about me because I've got 7.6 notes, but I don't have 7.5. Well, all righty, let's just make some 7.5 notes. Good grief. Y'all didn't know y'all got the crazy teacher this year, did y'all? All right, so 7.5, here we go. We're gonna make our own notes. And this is glide reflections and compositions. Okay, so it says a translation or glide and a reflection can be performed one after the other to produce a transformation known as a glide reflection. So we're going to say a glide reflection is a translation I'm going to put in parentheses after that a glide, a translation, and a reflection performed one after the other. Okay, so basically a glide reflection, just think about it, it glides and then it reflects. So it's going to slide and then flip, okay? So a glide reflection we'll think of as a slide and a flip, or a glide and a flip, however you want to remember that, okay? So, and again, it says it's a transformation in which every point P is mapped onto point P prime prime by the following steps. So step 1, translation maps from P to point P. So we have a translation from P to P prime. That's our first step. And then step 2 is a reflection over a line. This, it says line K, but I'm not stressed about that. I'm just going to say a reflection over a line parallel to the direction of the translation. So basically it's saying whichever direction my glide or my translation goes, then if there's going to be a line parallel to that direction, and then it reflects over that line. Okay, so this is where I go from P prime to P prime prime. Okay, so the first one, my translation, I glide and go from P to P prime. Then whichever direction I've gone to, there's a line parallel that I'm flipping over, and it goes from P prime to P prime prime. So my whole guide reflection goes from P to P prime prime. Okay, it goes through 2 steps, but it goes from P to P prime, from P prime to P prime prime. All right, so let's look at example 1. It says finding the image of a glide reflection. Use the information below to sketch the image of triangle ABC after a glide reflection. So let me flip back to my text. Not there. Oh, hold up. Y'all, I'm losing my mind. Okay, I don't know why. I just went ahead, we did our notes, and I just kept on moving from vectors and didn't even teach vectors. What is wrong with me today? I don't think I had enough coffee this morning. It's like it's Monday all over again. Go back. What? I don't even know what's wrong with me. I'm sorry, y'all. Go back to page 422. Go to page 422. Okay, we did talk about that the other day. So now go to Millie. 423, sorry. Let's look at 423. So we just talked about our vectors, and we talked about how come here. With our vectors, our units to the right and our units up, our units to the left. Good. Not my day, guys. I think I need a redo of today. I think I need to call it quits. Just kidding. You aren't that lucky. We only have 10 minutes left, and so good grief. It's been a day. All right. Good thing this is the only class I teach today, because I'm going to have to go back and reset. So what I will do, number 1, I will get those notes for 7.5 typed up. I will send y'all the notes for 7.5 and 7.6 as soon as class is finished. Okay, I'm going to send y'all those so you'll have them for tomorrow. Tomorrow is going to be a whole brand new day. All right. So we just looked at our vectors, and we learned about how basically if I turn it into a right triangle, I'm looking at its component form. Now let's go to example 3, identifying vector components. Okay, so we start with letter A. Notice we've got our vector JK. So if I wanted to determine its component form, again, like I said, I'm looking to see how many units I'm going to move this way. So I go 1, 2, 3 that way. And then I'm going up 1, 2, 3, 4 that way. So I can see that its component form is going to be 3, 4. For letter B, now look at B. notice that I have got a vertical vector. Now here, when I've got my vertical vector, instead of turning it into a triangle, it's actually going to become a horizontal. Okay. So when I've got my vertical vector and I look, notice that I don't have anywhere that I can go side to side. Okay. It's not moving side to side at all. So I have zero movement from side to side. Is everybody with me there? So I have zero movement from side to side. But what I do have is I have upward movement. So because I have zero movement from side to side, then my component form, oh, now we've lost April. I can try to get her back in. You there, April?
Yes, my connection was messed up.
That's okay. Hey, I'm about to chalk it up this day to just being, forget it. Okay, so we have our component form here. It did not make any side to side movement. Therefore, my first value is 0, but then it did go up 1, 2, 3, 4. So then it's going to be 0, 4. Is everybody following that so far? That if it's a slanted and I can basically make it into a right triangle, I'm looking at how many units do I go to the side and then up or down. So then that one is 3, 4. This one, I did not move anywhere side to side and I just went up. So it's 0, 4. And then looking at T to S, from T to S, I'm going down 1, 2, 3. So that would be a -3 down, but then I went 1, 2, 3 to the side. So remember, my horizontal is my first number. So that would be 3. Or actually, let me rewrite that. Let me write it a different way. Let me go ahead and write it as horizontal. Then I'm going 3 to the right and then 3 down. So I've got 3, -3. Okay, so do your horizontal first and then your vertical. Okay, so side to side, it moves 3 to the right. So that's positive, but then it goes down. Here comes Easton. We've lost him. All right. So notice that to be able to identify the component form, I'm just looking at what is my horizontal compared to the vertical. Okay. Any questions on A, B, or C on there? All right. Example 4. The component form of vector GH is 4, 2. Okay, so remember, this means I add 4 to X, add 2 to Y. Okay. So then it says use vector GH to translate the triangle whose vertices are at 3, 1, -1. I'm sorry, 3, -1, 1, 1, and 3, 5. Okay, so we can look at it on the picture, but also we can go ahead and look at it and know that if I am adding 4 and then adding 2, then I'm going to be at 7. A is going to be located at 7, 1. B is now going to be 5, 3. And C is now going to be at 7, 7. So we can see over here where they started with my blue figure. And then we have the translation and all they had to do. So we can see that my point A moved to 7, 1, B was 5, 3, C was 7, 7. So my component form helps me to start with my original ordered pairs. I use my component form to know, am I going to add or subtract to X, add or subtract Y to get my new ordered pairs for my translation. Any questions on that? So I use the component form to tell me how to change these values, my original values. If they're positive, you add, negative, subtract. All righty, and this one, it says in the diagram, QRST mapped onto Q prime, R prime, S prime, T prime by translation. Write the component form of the vector that can be used to describe the translation. So basically, I can choose a point. I'm going to look at T and T prime. And notice that I started with 9, 3. And I'm going to say, what did I do to 9, 3 to end up at 1, 5? So to get from 9 to 1, I subtracted 8. To get from 3 to 5, I added 2. So once I've done that, I'm going to look and see, is that correct? So I'm going to check my other points. So I'm going to look at Q and Q prime. So Q is 9, 0. If I subtract 8 from 9, I get 1. If I add 2 to 0, I've got 2. So that works for Q as well. So I can see that my component form is -8, 2, because I'm subtracting 8 from X and adding 2 to Y to get my new ordered pairs. So basically, example 4 and example 5 are kind of the flip-flop of each other. The first one, I start with my points, and I've already been given my component form to find my new points. Example 5, I have 2 sets of points, and I've got to identify component form. Okay. So in example 4, we use component form to find new points. In example 5, I have my 2 points, and I have to identify component form. Now in example 6, it talks about using vectors, and it just talks about how a boat travels a straight path between 2 islands, A and D. When the boat is 3 miles east and 2 miles north of its starting point, it encounters a storm at point B. The storm pushes the boat off course to point C as shown. So it says, write the component forms of the 2 vectors shown in the diagram. And then B says the final destination is 8 miles east and 4.5 miles north of the starting point. Write the component form of the vector that describes the path the boat can follow to arrive at its destination. So if we see that it started at 0, 0 and 3, 2, that's our vector. We can see that. And then it says that it went 3 miles east and 2 miles north. So our component form, we're adding 3 to X and adding 2 to Y. So now my component form, now B is 3, 2 and C is 4, 2. So we have vector BC, so we have to say 4 minus 3 is 1 and 2 minus 2 is 0. So now we can see that's our component form. The boat needs to travel from its current position, point C, to the island, point D. So to find the component form of the vector from C, which is 4, 2, and D, which is 8, 4.5, you subtract the corresponding coordinates. Okay, so CD, you start with 8, subtract 4, start with 4.5, subtract 2. So it's 4, 2.5. All righty, so then we get to the homework. And this is where we have the homework that I explained before I even taught the lessons. Okay, so this is where our homework is going to be numbers, what did I say, 15 through 33, odds, and then 39, 41. So 15 through 33 odds. Then we have 39, 41, and then jump to the next page, and we've got 45 and 47. All right, so sorry about my craziness today. We will hope that it will not be as bad tomorrow. I will drink more coffee by the time we have class tomorrow, and we will get through, we'll go back to our glide reflections and compositions. I will send y'all notes for 7.5 and 7.6 in just a little bit. And so you'll have time to print those out for class tomorrow. Okay. All right. I hope everybody has a good afternoon, and I will see y'all in the morning. Between now and then, if you have questions, please let me know, and I'll do the best I can to answer them and not make you more confused as I have done today.
Bye, Miss Jennifer.
All right. Bye, guys.
Thank you.
Bye. Thank you.